Okay, hi everyone. We are about to get started. Just a few logistics announcements. We are planning on, so I know assignment 3 is due and a lot of people are working on it. We're planning on releasing assignment 1 basically today or tomorrow. Assignment 1 grades today or tomorrow. Sorry, this takes a while due to various logistics things. Assignment 2, we're still grading, so it'll be a little while, but we're actually going to prioritize trying to turn around assignment 3 because that's really important for assignment 4. So we're going to try to give feedback on assignment 3 as soon as possible, probably by Wednesday next week. But I can't 100% guarantee that, but that's our goal. So are there any questions in the meantime? Okay. Sounds good. So I guess I will get started then. Today I want to talk about learning from and for knowledge bases. And one second. I normally have a screen up there where I can check my notes, but I don't have a screen up there. So you may see me look back a little bit more. So, but anyway, learning from and for knowledge bases. So knowledge bases, they're basically structured databases of lots of world knowledge that you can use. And the most common variety of a knowledge base contains entities, and these entities are like nodes in a graph. Relations are edges between nodes. And then there's a number of questions we'd like to ask about them, which is how can we learn to create and expand knowledge bases with kind of whatever learning methods we're using? And how can we learn from the information in knowledge bases to improve neural representations and use structured knowledge to answer questions? There's a bunch of different types of knowledge bases. The kind of original knowledge base that a lot of people used but don't really use anymore is WordNet. Has anybody used WordNet for something? I see one hand. The number of hands goes down every year. I ask this question. And basically, WordNet is a large database of words, including parts of speech and semantic relations between them. So we might have kind of artifact be the top level node in this hierarchy, then things like motor vehicle, motor car, compact, go-kart, and other things like this. This describes the relation between nouns, and the noun relationships between nouns can be things like is-a relations, like a hatchback is a variety of car, part of relations, like a wheel is a part of a car. There's also a type and instance distinction. So a car is a type, or an airplane is a type, and Air Force One is an instance, for example. So there's verb relations. Verb relations are ordered by specificity. So communicate is a type of talk, and talk is a type of communicate, and whisper is a type of talk. And for adjectives, we have antonym relations between them. So this used to be really, really popular. It used to be, factor into all of our processing of natural language. Any idea why this is not as popular anymore? Embeddings. Yeah, so we have word embeddings now, and word embeddings get us most of the way there for this sort of thing. They don't get us all of the way there, which is why knowledge bases are still helpful. And I'll explain a little bit more about that in a bit. Another kind of old school knowledge graph, which actually came from well before 1995, is something called Psych. And it's a manually curated database that attempted to encode all common sense knowledge. And they built it for like 30 years. And so they had this very extensive hierarchy of like all things, and then you have the intangible things and individuals. You have information about plans and goals, actors, actions, agents, organizations, human activities, and things like this. And then on top of that, you had a bunch of domain-specific knowledge and domain-specific facts and data. This actually stopped being used well before large language models. But does anyone have an idea why they stopped using this, or why this never really became a huge thing that lots of people used?
think it's still a commercial product. It's not widely known.
Yeah, it's kind of a commercial product, yeah. And but any ideas? Basically, the reason why is it's completely impossible to encode all of human knowledge by hand, right? It was just too ambitious. You can get to having a lot of all of this knowledge encoded by hand according to rules, but then you have exceptions, and then you have exceptions to the exceptions, and all of those other things like this. And it's just too much to possibly do without some sort of kind of learning and also some sort of good knowledge representation for all these things. So I think what we've done nowadays is actually with large language models, we've kind of given up on encoding much of this knowledge declaratively, like, common sense and reasoning and other stuff like that, and are largely kind of relying on LMs for that. But there's other segments of knowledge that language models don't pick up extremely well, and there's still some benefit in using structured knowledge bases. And one variety of this is like entity knowledge. And the reason why is because there's so many entities in the world. There's so many entities in the world that it's pretty hard for even very large language models to memorize all the facts about them. The facts are changing all the time. So, what is the name of Carnegie Mellon University has changed at least 4 times. It started out as the Carnegie Technical Schools, the Carnegie Institute of Technology, Carnegie-Mellon University, and then it changed to Carnegie Mellon University with no hyphen. So I bet you didn't know about this distinction, but it is a distinction that changed in 1988. So, but basically, in order to encode this entity information, there's a really powerful data source, which is Wikipedia. And Wikipedia is created by a very large number of contributors. It's updated all the time, and it has these structured boxes here that are like created in easily parsable markup. And because of this, you can extract a lot of information from here. And notably, there are also links between Carnegie Mellon University and private university established in 1900 by Andrew Carnegie, and a link to Andrew Carnegie. And from this, you can extract all of these kinds of structured pieces of information. There's also further expansions of this. So there's something called BabelNet, which is focused on getting this entity information from data sources like Wikipedia and WordNet, but making sure that it works across languages. And then finally, the most common database that people use is Wikidata, which is a curated database of entities linked and extremely large scale. It's multilingual. So you can go in and search any information that you have about any entities. Does anyone have a favorite entity of the day, hopefully not about politics, that you would like to look up information about? Entity 42. Okay. Is that the US?
The code is 42. Like the ID is 42.
Yeah, I think that's the United States, right? Or is it? That's
Give to Adam Douglas.
Oh, really? Let me see. Oh, Douglas Adams. Oh, okay. Interesting. I didn't know that. Sorry. The United States is something very similar. It's a short entity. But yeah, Douglas Adams is entity number 42 within Wikidata. Did people read Hitchhiker's Guide to the Galaxy? Yeah. So you'll understand the joke if you did. 42 is the answer to the question about life, the universe, and everything. But if we browse through here, you can see Douglas Adams is the name in English. And then we have in more languages. So if we look at all the languages, we have Douglas Adams in. a very large number of languages. And so this is good as like a multilingual dictionary. Douglas Adams is an instance of human. And this is stated in the BNF authorities and in other places like this. You get an image of Douglas Adams. You get Douglas Adams's signature. You get sex or gender being male, citizenship, lots of other pieces of information like this, date of birth and things. So basically, you can see there's lots of structured information here. Does anyone have a somewhat more niche entity that you'd like to ask about? Any ideas? Let me do Ed Gainey. So Ed Gainey is, of course, the mayor of Pittsburgh. So you still get a picture. You get male, United States of America, date of birth, a fair number of things, party and stuff like that, but not anywhere near as much as Douglas Adams. And you go with a more niche entity. You get my name in English and Japanese. If anybody wants to put my name in Chinese or something, you can make a contribution to human knowledge. I'm human, I'm male, first name, university teacher, computer scientist, field of work, natural language processing. And it has my doctoral advisors. The interesting thing is the reason why it has my doctoral advisors is because like when I was a PhD student, I entered my my information in the mathematics genealogy project, and it somehow pulled all the information from the mathematics genealogy project. So it's pulling information from many different sources there. Cool. Anyway, so there's lots of information in there. Another thing is you can add more information. This is all manually curated, so you can contribute to it, et cetera. Cool. The next thing I'd like to talk about is querying structured data. Any questions, or maybe it's straightforward? Yeah. So next thing is about querying structured data. So last night I put this in Google and I asked who are the prime ministers of Japan, and based on this, Google gave me an output, Japan prime ministers, and it basically listed up all of them. It has all of their pictures and things like this. And essentially, the reason why they're able to do this is that Google is basing their search on querying this structured data. A bit of a backstory behind Wikidata is it actually used to be called Freebase, and Freebase was created by a company that was trying to collect all this data together, and Google basically bought Freebase and then opened it up as a community project for maintenance later. But because of that, the utility of the structured data is helpful. One interesting thing I've noticed is the amount that Google seems to be using this structured data is relatively minimal. So like if I ask it a slightly more complex question, like what are the past 5 prime ministers of Japan? It does not give you the past 5 prime ministers of Japan, despite the fact that you could do that with Wikidata. It instead just falls back to doing normal question answering. So, and it actually didn't do a particularly good job of answering this question. It gave me the last 5 eras of Japan instead of the last 5 prime ministers of Japan. So I hope Google fixes that issue. But like, how do we query structured databases? I think probably everybody here has heard of or probably used SQL, SQL at some point. For querying these structured knowledge bases, there's a query language called Sparkle. And it looks a bit like this. It looks similar to SQL, but it's a little bit different. So we have like select this, and this is a query finding the prime ministers of Japan in descending order of their start date. And so basically what it's doing is it's saying, okay, I have a prime minister, and they have held a position, and that position is the prime minister of Japan. And then you have optional start dates, optional end dates, and then you order by descending start date here, and you return the answer in English. So this gave me this answer here. So you can get all of these, and then presumably you could also add the image and other stuff like that. So under the hood, that's almost certainly what Google is doing to answer these questions. If you want to try this out yourself, there's this web page where you can do that easily. I can just put in one of the examples. So who likes cats? Okay. Who likes horses? Who likes cats with pictures? Yeah, I do too. So we can run that query. That gives us
Oh my God.
lots of cats and pictures.
Fucking president.
It's and apparently also the president of Indonesia. So new president of Indonesia. These are I don't know if these are cats with pictures or pictures of cats, but we also get cats at the White House and cats wearing costumes and stuff. So if you want your daily dose of cats, you can write a Sparkle query to give you cats with pictures. So yeah, and you can just search for Wikidata query service to find that. So how is this useful? I would say that there's two reasons why this is useful. The first reason is that you can directly query Wikidata and show it in a structured format, like I just did in like a table or in the Google search results or things. There's also papers that demonstrate that you can use essentially Wikidata or Sparkle queries to condition large language models. So this paper demonstrates that if you have GPT, you can initially augment something like where did Bronx take place? And it will do entity linking to Wikidata and find a Bronx tale. And then based on the entity linking, it will generate the Sparkle query for you. You get the response. If you get a positive response, this can be generated directly from Wikidata. If you get a negative response, you can generate it from GPT. And basically, they demonstrate that kind of in a setting like this, you can greatly reduce the amount of incorrect data that you have through GPT. This paper is a little bit old, so this is back when GPT had more hallucinations and stuff like this. But I think one thing you'll notice is if you try to use GPT for kind of very long tail things or things that are a little bit out of the normal domain, it will hallucinate a lot anyway. So I think this is one way to improve the amount of trusted information that you can get. Cool. Any questions here? This can be a good tool if you're like actually trying to build practical systems. So the next thing I'd like to talk about a little bit is probing factual knowledge within language models and trying to figure out whether language models are able to effectively answer factual queries. So in contrast to taking a language model and using it to generate a Sparkle query or something like this, this is the opposite of seeing whether the language models are able to do well in finding stuff from kind of that is included in knowledge graphs. So traditional question answering or machine reading and comprehension models usually refer to things like Wikipedia articles or knowledge graphs. But we would also like to know whether they already capture this variety of knowledge. So there was a paper in 2019 that was kind of a initial start to this, which was language models as knowledge bases. And so what they did is instead of doing this sort of Sparkle style memory access, we asked, or not we, they asked the same questions, but they just asked in natural language. And they had a masked language model try to fill in the information. And in 2019, it was kind of like a big, interesting result that language models had lots of knowledge in them. Now, maybe not so much. But the basic querying methodology that they used is still relevant, which is you you take a knowledge base that's full of long tail entities, you textualize it, and then you measure whether the model is able to generate those textual entities. And like, let's say you wanted to measure the ability of language models to give you answers about things that happened in 2024, for instance. Like, let's say you wanted to check whether language models knew facts about events that happened in 2024, 2023, 2022, 2021. All you need to do is you need to write a Sparkle query to find events that happened in those years because that's included in Sparkle, and then generate a test data set from that. So this is a very flexible methodology that lets you answer a lot of questions. Specifically, the way they did that here was they created manual prompts for 41 relations. So like X was founded in Y. They filled in the subjects using, and then had LMs generate the outputs, and they found that BERT was able to answer 31% of these questions. One issue with this data set, though, is they only focused on things that were a single token in the language models that they were probing. And in reality, the answer is usually multiple tokens. So like this excludes United States of America, for example, which is, not a great idea if you're trying to probe factual knowledge, because a lot of knowledge is about the US. So there were some issues with their methodology here that have been fixed in future ones. So this is one of the papers that my student Zhengbao Zhang did in 2020. And what we tried to do is we tried to probe the cross-lingual competence of language models to answer factual questions. And I think this is really interesting. It has a lot of kind of implications because here we're probing factual knowledge, right? And like factual knowledge, it's knowledge, and humans, if you know one thing in one language, you also know, you also still know it, despite the fact that if you're speaking another language, although maybe you wouldn't be able to, generate it appropriately in the other language. But what we found is essentially that the language models were much better at answering factual questions in English than they were in other languages, and that kind of went down with resourcedness. And another interesting thing is we tried really hard to kind of get rid of this language effect. We did like code switched training and all of these other methods, and we weren't able to do it, which kind of indicates that like knowledge, despite the fact that it's in the models for things like English, it just isn't as accessible if you query them in other languages. So I think that has some pretty interesting implications. So this is one method that has been used to improve the ability of language models to answer factual questions. So the basic premise behind this paper is essentially that language models have the ability to access knowledge. They have a lot of knowledge, and it's not easily accessible, which is also kind of demonstrated by this this paper here. And essentially what they did is they created a model called Unified QA, where they trained on lots and lots of question pairs and evaluated on kind of the outputs, and evaluated on the ability of models to answer questions directly from their parameters. So this was kind of a predecessor to broader instruction tuning, which we do nowadays, but it kind of was the first demonstration that you could answer a lot of different questions directly from the model's parameters if you had a significantly large model. And another thing that people have found is even if you're not using a knowledge base, non-parametric models outperform parametric models. So these are models that allow you to retrieve or do RAG. And this might be kind of obvious. It's like if you have access to a RAG data store, you're going to do better. Like you did this in assignment 2, so you should know this. But one interesting fact is that models with a RAG data store tend to do better, even if the RAG data store is just the data that they were trained on. So there, over and over and over again, people have shown that language model training, just training the parameters of the models, is not as effective as doing some sort of RAG over the original data, no matter how big you make the models. Cool. Another thing that we examined in one of our works is multi-hop factual reasoning in LLMs. And this is another thing where the results were unfortunately a bit negative. And but I think it points to an important issue in whether models are able to effectively generalize from knowledge that they have. So what we did here was we also did a similar probing paradigm where we had we had one question and then we had another question, and then we tried to combine them into composite questions that test whether you're able to kind of reason over implications of particular pieces of factual knowledge. And we did this in a number of different ways. We did basically composition, conjunction, superlative, comparative, which are all kind of different ways of composing together different pieces of factual knowledge. And what we found is the way to interpret this figure here is 0, 0 is basically like each of the component questions was not answered correctly. 0, 1 is each of the second component question was answered correctly, but the first one was not. 1, 0 is the first question was answered correctly, but the second was not. And 1, 1 is both were answered correctly. So like one interesting thing that we found was, and then the orange is that the kind of like multi-hop question was answered correctly, and the blue is, orange is the multi-hop question was answered incorrectly, and the blue is the multi-hop question was answered correctly. And what we found here is that if you answer both of the questions correctly, both of the component questions correctly, you generally get the full one correct. Not surprising, that's more or less what you would expect, right? If you can answer the first question right and the second question right, you should be able to get the kind of composite question right. If you get both of them wrong, or you get the last one wrong, then you could essentially, it would be rare that you would get the full multi-hop question right. But if you get only the second question correct, then that's very strongly indicative that you would get the full composite question correct. So this is interesting. Why is this interesting? So look at this composite question. Which part of Georgia? Just ignore the rest of this. And let's say I just said which part of Georgia. If you answered Atlanta, you would get it right a lot of the time, right? So you can kind of, even without knowing anything about where the artist that recorded Party Ain't Over is from, you can still answer the question right by just guessing Atlanta. So and then at the same time, it's not necessarily the case that if you get both right, you'll get the final question right either. So there are cases where you know each of the component answers, but can't get the final one right. So a better way to benchmark this is like an interesting open problem, but I think how we can combine together multiple pieces of knowledge is an interesting research topic. Cool. Any ideas or questions here?
So.
Yeah.
The previous slide, so it seems that this isn't still a good benchmark because of there are spurious, there are just some questions where you can guess the correct answer based on like only the second question.
Yeah, I think probably what we would want to do, so, this was what we did in the scope of one paper. It took a fair while to, arrive at this result in the first place. Probably what I would want to do if I were to continue using this as a benchmark is, you might want to filter out the ones that you get right, seriously. This is generally a good idea when you're making a benchmark. Like, let's say you're making a vision language benchmark. If you can get the question right without vision, you should probably remove that question. So I think that's what I would do here. It's not hard to do, I guess. But I think that would be one thing. Yeah. Cool. So the next thing I'd like to talk about is knowledge-based completion. So, as I mentioned, knowledge bases can be useful for, querying. They can, you can use structured queries over them to get information. You can get, you can sort, you can do all kinds of other things that are not super easy to do. But even for extremely large scale knowledge bases, they are by nature incomplete. And so there's a lot of information in there that doesn't exist. And so in Freebase or Wikidata, 71% of the humans were missing a date of birth. And like in Wikidata, my entry did not have a date of birth. But I promise I was born at some point. And so the question is, can we perform relation extraction to extract information for knowledge bases? So given particular entities, are we able to identify relations between them? And there's a number of ways that people do this. There's kind of the one interesting way and then a kind of practical way of doing this. I'm going to maybe talk about the interesting way first, and then the practical but a little bit messier way after that. But basically, we talked about consistency and embeddings from the point of view of WordNet and why people don't use WordNet anymore, because, we can get things about words through consistency and embeddings. But if we're talking about a knowledge graph, we're talking about a whole different scale. We're talking about like millions or, tens of millions, hundreds of millions of entities. Actually, I'm not sure what the size of Wikidata is nowadays. Let me see. Yeah, so Wikidata has 114 million entries in it. So that's pretty extensive. And so that's kind of a different game than, just dealing with word embeddings. So the first challenge is, how can you learn embeddings for each of the entities in a knowledge graph in the first place? And the way they do this is essentially they express triples as additive transformations and minimize the distance between the distance of existing triples with a margin-based loss. And so this is the best way of kind of expressing this, which is you get an embedding for each entity. And the way you can get embeddings for entities is various. Actually, I probably should have had this on the first slide, but the way that people get embeddings is various. The most common way of doing this is to do something like a word-to-vec style objective where you predict the surrounding words based on the word in the middle. And this can be used to calculate word embeddings, but it can also be used to calculate entity embeddings. And the way you calculate entity embeddings with this is you replace each entity in Wikipedia. So each entity span in Wikipedia that links to another Wikipedia page with an embedding for that entity. And that works because Wikipedia has a ton of links between all of the pages. So you can use that as kind of weak supervision that that entity is about is about a particular page. So if you do this, then you essentially can train an embedding for each entity in the first place. But the problem is, let's say you have those entity embeddings. Number one, they might be, they might not be completely sufficient because, a lot of the entities will not have very many mentions in Wikipedia, for instance. The other thing is that doesn't tell you anything about relations. And so what you want is you want better embeddings of these entities. And you also want to learn relation vectors that tell you whether two entities are in a particular relation with each other. So how do you optimize something like this? One way you can optimize is basically by taking a head entity and a tail entity. And based on the head and tail entity, you learn this, this vector between them, where you try to make it so that all entities that are in this relation get a higher score, and all entities that are not in this relation get a lower score, essentially. Sorry, just making sure that I got that right. Yeah. And so you create and so then you can use that to train this this vector here. And this vector is called R here. It's called L here. It's because I took the figure from a different paper. But this is very, very simple, but it allows you to learn something that expresses the relations between entities. And then what do you do when you want to find a new, you want to find something new? Like, let's say you wanted to find out where I was born or something like that, and that is not in Wikidata. What you would do is you would then take the embedding for Graham Neubig, and then you would take the relation embedding, and you would try to find the closest location that might give you something that you could fill up, and maybe you could then go in and confirm that manually and add it to Wikidata or something. This is kind of oversimplified though, and the reason why it's oversimplified is number one, or maybe the biggest thing is not all dimensions are relevant to a particular relation. And so if you have entity embeddings, then this can actually cause a lot of noise to be added because you need the relations to, exactly match in all dimensions. So the solution that people have proposed is basically to project the entity vectors on a hyperplane specifically for that relation and then verify the relation. So this is what it looks like. And so you would have this projection onto a different hyperplane. And then after you did that projection, you would have the vector between them, and you would verify the vector in that space. So just to give an example of why this is useful, basically what this can do is this can remove all information from the entity and from the location that, or for example, let's say we're talking about entities. You could remove all the information from the entity that is not related to location if you wanted to find where that person was born. So you would remove all the stuff about when they were born or what jobs they did or things like that. And so you could just focus on solely the information that's useful for inducing the relation. So this one's using just vectors to produce, to project, and transr is another further example that uses a full matrix. I might skip over this a little bit. Basically, it's a more expressive method of doing that. So all of these are methods where like you calculate entity embeddings, and then based on the entity embeddings, you try to find relations. So there's a completely different way of extracting relations, which I think is maybe a little bit more practical, but a little bit more messy also, which is specifically extracting relations from individual mentions of text. So basically what you do is you start out with a seed set of entity relation entity pairs. So this could be like all of Wikidata nowadays, for instance. And you extract all text that matches this and use it to train. And So the way this works is like, let's say we have Steven Spielberg in Saving Private Ryan, and Steven Spielberg is the producer of, or sorry, is the director of Saving Private Ryan. And so you would extract all sentences that have Steven Spielberg and Saving Private Ryan in them and treat them as positive training examples for a relation classifier that identifies director of relations. And so if you did that, now you get this one is a training example and this one is a training example. Do these look like good training examples for the director of relation? Any ideas? Is number one a good example? What about number two? Yeah, two is better. Two is a good example because it says directed by. So it's like, this is very obviously indicative of, this being a good relation. This one is not, because Steven Spielberg's film could mean he's the author of the film, the screenwriter of the film, the producer of the film, the actor in the film. It could be any of them. So you basically create a large corpus of noisily labeled text to train a system, and then you run this over the entire internet and extract all the director of relations. And of course, this can cause issues because it's noisy. So another option is just doing supervised relation classification from training data. And you can train whatever model you want to do this. You could train a span-based classifier using something like BERT, or you could train an LLM. I would highly encourage you not to train an LLM to do this because you want to run it on the entire internet. And running an LLM on the internet is expensive, even if you're OpenAI. So maybe don't do that. And actually, even back in these days, they were saying that like running a parser is too expensive. So we want to just do it with a kind of like span labeler. So you definitely want to make that inexpensive. If you're creating these sorts of classifiers with weak supervision or distant supervision, weak supervision and distant supervision basically mean the same thing. The original paper called it distant supervision, but the more common way of calling it is weak supervision. But one really interesting thing is, how do you model noise? So there's a lot of different ways to do this. This is just one example. One example is that you have a model that is essentially trained on trusted data. And then after you've trained the model on trusted data, like a small supervised training set, or no, sorry. You train the model on lots of data. And you have a small supervised training set where you have like actual, can calculate the predictions directly. But then separately from that, you have like a noise modeling transition matrix that allows you to kind of modify the probabilities so that they more closely match the actual distribution in this small data set. So you would create this predictor from noisy data and then have a transition matrix here to model the noise. They add some things like trace normalization to make the matrix close to the identity matrix to try to make the transition matrix not be too crazy or too flat. But this is an interesting way of doing it. Another thing that I should have mentioned, but I didn't mention here, is there's a lot of iterative methods. And the way the iterative methods work is you start out with like this noisy supervision with a small database. You train a classifier and then you extract very high confidence pairs. And the way you get high confidence pairs are pairs that are very frequent. So like Steven Spielberg, director Private Ryan is very frequent, and you don't have a frequent alternate director for Private Ryan. So like whenever you see Private Ryan, whenever you see Saving Private Ryan, you select the director as Steven Spielberg. And that gives you a high mutual information between the two, between Saving Private Ryan directed by and Steven Spielberg. So if you do that, then that's, very trustworthy, and you filter out all the untrustworthy ones, and then you do an iterative training process where you use the new knowledge base to do more training. So there's a lot of stuff in there. There's probably too much for me to cover here, but if you're interested, you can look more into it. So yeah, this is one step in knowledge base completion. Are there any questions or clarifications or things? Okay, cool. So another thing that you can do is you can model relations themselves. And so word embeddings or noisy data extracted from the internet are somewhat indicative of relations existing, but other relations or combinations of them are also indicative. And so this is basically a link prediction problem in graphs, which is like given a whole bunch of links, can we predict the other links in the graph? And interestingly, one of Ilya Sutskever's earliest papers was on knowledge base completion. So you wouldn't guess by him creating like GPT-3 and GPT-4 and everything else in OpenAI. But basically, this paper was on modeling relations by decomposing a tensor containing entity and relation entity tuples. And the way this works is you basically do a low rank decomposition of the tensor. And based on this low rank decomposition of the tensor, you turn it into very low rank, and then you explode it back into the original tensor. And any things that have a high, it's basically a tensor with a lot of a very sparse tensor with a lot of like 1, 0 values. And then you do a low rank decomposition, and then you blow it back up. And then if any of the values have like a high value in the decomposed and blown up tensor, then these are ones that are likely to like actually exist, despite the fact that they weren't included in the original tensor. So that's one thing that you can do here. This is also really common from like recommender systems, if you've ever studied recommender systems. So it's the way, Amazon recommends new things for you, Netflix recommends new things for you. You try to find this person likes this movie, you do a low rank decomposition and blow it back up. And then if you get a high recommendation, you'll see it in your Amazon or Netflix feed. Okay. Another interesting thing is modeling relation paths. And the way this works is you have multi-step paths that can be informative for indicating individual relations. So I like this. I like this task that they're solving, which is given a particular word appearing in a paper, recommend the venue in which to publish the paper. And so what they have is they have a whole bunch of instances from a knowledge graph, which is like paper was published in. And so then they extract additional paths that are kind of like have high mutual information with this. So here you have the word in the paper title is in the title of another paper that appeared in the journal. So that's indicative of this relation, or of a paper being published in a journal. Or the word is in the title of a paper where there is a first author of that paper who published another paper that's in that journal, and things like this. So you can go through all of these, and these become gradually less informative, but if you really want to pick up kind of recommendations or whatever else based on paucity of evidence, then this could be helpful. Yeah, this is basically a trainable version of what I talked about before. So they called this differentiable logic rules, and they essentially consider paths that entail relations. So you have like city and country, and has office in city entails has office in country most of the time. And so so you can also do this, and they come up with an optimization algorithm that allows you to specifically optimize the values of the transition matrices that specify, how likely this implicature is. And this is good, specifically because, like, as I mentioned at the very beginning, things like psych failed because there's like exceptions upon exceptions. And if you have those exceptions upon exceptions, then, your knowledge base is never going to be useful because, it's wrong some of the time. And so this basically gives you the ability to kind of take that into account. One other thing I should mention that I didn't put on the slides is, if you're really interested in this, if you're interested in knowledge and reasoning and soft logic and things like this, which I think are very interesting topics, kind of. So there's a lot of interest in like reasoning in large language models. Like Shang did a whole class where he talked about a lot about, logic, not logic, but reasoning style tasks like math and code and stuff. But if you wanted to connect this more to formal logic, there's also another interesting keyword called Markov logic, which was briefly popular, but became unpopular due to like scalability issues and estimating the models and stuff. But if you're interested in this general idea of like reasoning and implicature and stuff like that in language models, that might also be worth taking a look at. Cool. Any questions here? Yeah.
Papers is there just not a lot of work in this space recently?
I'm going to be talking about. Yeah, I think there's a couple answers to that. Like I did talk about more of the newer papers in like the probing language models for factual knowledge stuff. I feel like there's two things. Number one, there is less work in this area overall because people have been focusing on kind of on language models and a lot on specifically machine reading and stuff like this. Another reason is maybe kind of just selfishly, I've worked on this a little bit less in the past couple years, so I haven't gone through an extremely extensive literature review, but I think it's still very relevant because, one of the biggest problems with language models nowadays is hallucinating data in kind of low resource settings, and people have been focusing on this not from the point of view of structured data, but from the point of view of improving their ability to process unstructured data. And honestly, I've seen a lot less work on doing it in this area, despite the fact that I think it's a promising direction. So yeah, maybe that's an answer or not an answer, but yeah. Cool. Okay, so another thing I'd like to talk about is schema-free information extraction. And the kind of seminal work in this direction was open information extraction. And the basic idea is when you extract relations, you don't have a fixed schema of relations. You don't have like 41 relations or 200 relations or 500 relations as specified in Wikipedia. But the basic idea is that the text itself is the relation. And so if you have something like this, you have United has a hub in Chicago. You have United, and then the relation has a hub in. And you have Chicago. But the problem with this is you have like Chicago is the headquarters of and United Continental Holdings. And this allows you to extract any variety of relations. But the problem is it doesn't abstract to new relations. So these say the same thing, essentially, but you aren't able to detect the fact that they say the same thing by just looking at the relations themselves. And so for open information extraction, you actually almost don't need a model to do open information extraction because the text itself is a relation. There's not a whole bunch of ambiguity here. And so they use a parser to extract according to rules. And so each relation must contain a predicate. The subject and object must be noun phrases, etc. And then they train a fast model to extract over large amounts of data. And as I mentioned before, aggregate multiple pieces of evidence. So if you're seeing a fact over and over and over again, you assume that it's a kind of reliable fact. There's also, this isn't perfect though, because you do get some like kind of awkward looking relations. And there's an interesting paper that demonstrated that you could actually create relatively large data sets for training these sorts of open information extractors by asking crowd workers simple questions. So for instance, if you have UCD finish the 2006 championships as Dublin champions by beating St. Vincent's in the finals, you can ask things like who finished something, what did someone finish, what did someone finish something as, how did someone finish something, and etc. And this allows you to extract training data from these sentences. And this can be converted into OpenIE extractions for use in training a supervised classifier. So then the question becomes, like, what if you have a whole bunch of open extractions? What can you do with them to create a more structured knowledge base? And there's an interesting work called universal schema. And the basic idea is, let's say we have a couple databases, like we have Freebase or Wikidata, and then we have a different database called TAC, and then maybe we have a different one that's like specific for medical tasks or legal tasks or something like this. And then we have all of these open information extracted kind of corpora, not corpora, sorry, relations. What we do is we turn all of these into a big tensor. And then based on this big tensor, we do the same thing that we talked about before. We do tensor decomposition, a low rank approximation, and then blow the tensor back up. And based on this, we then get things where we have like 0.95 or 0.05 or things like this. And this allows us to fill in the missing relations. And this can allow us to, for example, link open information extraction into the structured databases for entities that we don't have in the structured databases. It could also allow us to link the similarities between, professor at or historian at an employee. And we can find the similarities between the relations that are extracted through OpenIE and in the actual database. And one interesting thing also is this could guide you in the direction of finding relations that aren't included in the structured database. So it would allow you to expand to new varieties of information as well. Okay. The final thing I'd like to talk about is using knowledge bases to inform language models. So this is actually informing embeddings. And so basically, let me make sure. Okay. So there's a fair number of methods like this. This is kind of an older one, but you can also, there's also some newer ones that work on kind of contextualized embeddings, but this works on word embeddings. And basically what they did was they took the relations that were included in things like WordNet, and they tried to force models to make the embeddings closer if the words were synonyms in a structured knowledge base. And I'm going to talk about this next class when I talk about multilingual learning. Another way you can do something very similar is you can align things across languages if the words mean the same thing across languages. So you basically add a regularization that tries to push things closer together if they're synonyms. One interesting thing, which is maybe possible, but also possibly questionable, is they try to force antonyms away from each other. So WordNet annotates synonyms and antonyms. The problem why this is questionable is actually things like love and hate appear in similar contexts a lot, so you might not necessarily want to force them away from each other, but it's one method that exists. There's also methods for injecting knowledge into language models. So this is one of my own papers. I have to admit, this is not the most widely cited paper. So I probably wouldn't be introducing it if it wasn't my paper, but I like it. So that's my prerogative for teaching this class. So apologies. But basically what we did here in this paper was we made it possible to not only generate words, but also generate entity tags. And so if you generate the entity tag, you can generate like birth name or given name or family name. And you can create supervised training data for this. In this paper, we did something rather complex, which is we had like a dynamic programming algorithm that, specifically allowed you to optimize over all of the paths. But even if you didn't do this, another way you could do this is you could if you identified birth name, you could sample birth name and inject it into the training data or other stuff like that. So I think there's a lot of different ways to do this. But the reason why this is cool is this would give the language model the ability to predict, like, whenever a birth name was present, you could predict birth name and you would be guaranteed that it would not, predict something else. Another thing is this is kind of an interesting paper from the point of view of the approach it takes. It's also one of my papers, but it essentially creates a way to use a text corpus as a RAG index while considering the relations between different entities. So the overall goal here was to create a RAG corpus where basically you would embed a question, and after you embedded the question, you would have embeddings within the corpus where the embeddings of the answer to the question are optimized to be close to the embedding of the question itself. And so if we had Grateful Dead, sorry, actually, that's not the best example. So when was the Grateful Dead and Bob Dylan album released? We would annotate a large text corpus and with relations and entities, and we would try to optimize the entity of the date of release. We would try to optimize the entity of like Bob Dylan country question mark to match well with American, and the entity of Bob Dylan profession question mark to match well with singer-songwriters. So you would generate a query, and the query would match to Bob Dylan country question mark. And then within the knowledge base, American would also be optimized to match well with this. So this would allow you to kind of directly look up these facts more effectively than you would if you were optimizing this implicitly. And the good thing about this is, again, we can create tons and tons of weak supervision data for this, right? Because we have a knowledge base, we have all the data with these knowledge base relations annotated. So this allows you to create more effective retrievers for kind of fact-based questions. There's also included in here an iterative process that does multi-hop questions, but actually I think that's maybe the less important part. I think the more important part is kind of this method for optimizing the retrieval index.